Hello students, we are going to study the longitudinal vibrations of a bar in this lecture. In this figure, we see a bar which is having length L and it is aligned with the x-axis. The displacement of the bar takes place also along the x-axis and is given by u, which is a function of x and t. We take a small elemental length of this bar dx, and we are seeing here a enlarged view of this particular element. We can see there is a force of magnitude p acting on the left hand side, while the force of magnitude p plus dp is acting on the right hand side. Because of this bar is having a displacement u at the left hand, while on the right hand the displacement is given by u plus du. So the net deformation in this bar is du and the original length of this element is dx. Now we define few terms here. The A is the cross-section area of a bar. In case the bar is of non-constant cross-section, then it will be also a function of x. P is the axial force which is acting on the bar. Rho is the mass density. F is the external force that is being applied, and it is given by external force per unit length. And E is the modulus of elasticity of the bar. We are going to apply the Newton's second law along the axial direction for the forces equilibrium, and the first force that we have here is P plus dP, which is acting on the positive x direction, so it is shown here. Then we have another force P acting in the opposite direction, and it is here, and the external force F per unit length. Therefore, for this particular element, the external force value will be F dot dx. Now the algebraic sum of these forces should be equal to the mass times of acceleration. As rho is the mass density, so rho dot a dot dx is going to be the mass of this element. As u is the displacement, so its second derivative with respect to time will provide us the acceleration. So del square u by del t square will be the acceleration here. Now, from the strength of material, we know that stress sigma is given by force applied divided by the area. So that is P by A. So from this we can write the value of force P as stress multiplied by area, and stress is nothing but the modulus of elasticity multiplied by the strain. As du is the deformation and dx is the original length, so del u by del x is going to be the strain here. We also know that the change in force P dP can be obtained by multiplying the rate of change of P with respect to x with the length in question, that is dx. We are going to substitute equation 3 into equation 1. So this will provide us with this equation, and when we substitute equation 2 into this equation, we will obtain the equation 3. Now equation 3 is for the non-homogeneous, non-constant cross-section longitudinal vibration of the bar, which is subjected to the force vibration. In case if the bar is of constant cross-section, the A area will no longer be function of x and can be taken out of this derivative. Similarly, if the bar is of homogeneous material, the E can also be bring out of this differential. So what remains is EA del square u by del x square plus F equal to rho A del square u by del t square. Now the equation 4 that we see here belongs to the homogeneous constant cross-section bar force vibration. In case the bar is having free vibration, that means external force F is 0, this equation get reduced to this equation, and finally we get our familiar wave equation by using C is equal to under root E by rho. Now this is identical equation to that we obtain in case of string, except the difference is in case of a string equation the value of C was given by under root P by rho. Here E is the modulus of elasticity and rho is the mass density of the bar material. So solution of this wave equation 5 will be similar to what we obtain in case of a string. So that means we are going to apply the method of separation of variable, and we are going to assume the solution as made up of two parts, one dependent on space x only, other dependent on time t only, and we will obtain two ordinary differential equations whose solution will be given by a cos omega x by c plus b sin omega x by c and c cos omega t plus d sin omega t. Now we can obtain the value of a and b using the boundary conditions, and for the case of bar these boundary conditions can be either u can be 0 at one of the end of this or both of the end of the bar, or its first derivative with respect to space may be 0, that is del u by del x. Here in this table all these possible end condition of the bar is shown. So one can see the fixed free bar, free bar and a fixed bar. In case of fixed free, at one end the u will be 0 and the other end its first derivative with respect to x will be 0. In case both the ends of the bar are free, then the first derivative of u with respect to x will be 0 at both the ends. If both the ends are fixed, in case u will be 0 at both the ends. By using the method of separation of variable, we can obtain the frequency equation, and these frequency equations are given in this table, and we can also obtain the mode shapes. Using the frequency equation, one can determine the natural frequencies as shown here. You can note here that the frequency equation for both free and fixed are the same, but the natural frequency values in case of free start from the value 0, while in case of fixed they start from the value 1. It is because in the case of free vibration the first natural frequency will be 0, and it corresponds to the mode in which the body is moving completely either to the left hand side or to the right hand side as a rigid body. That's why this particular mode is termed as rigid body mode, while such rigid body mode is absent in case of a fixed beam. Now it will be a good exercise to determine all these frequency equation on your own using the method of separation of variable as an assignment. Thank you.